Circulating levels of bile acids are elevated in a mouse model of longevity. So first, let's have a look at the mouse model of longevity. Here's survival data for control animals and lit mice, which are in black circles. These are animals that have a mutation in the growth hormone receptor, thereby leading to 99% reduced levels of circulating growth hormone. So when looking at survival, median survival is indicated by 50% survival. This is when half the colony has died, half is still alive. And maximum survival, this is 10% survival. This is when 90% of the colony has died and only 10% is still alive. We can see a significant increase for both median and maximal lifespan in the lit mice, which are otherwise known as dwarf mice or little mice. So we can see that circulating levels of bile acids, as I've written here, are elevated in this mouse model of longevity. And we can see that data there. So here are 7 bile acids as contained in blood for the little mice, for wild type mice, and the ratio between the little mice, the dwarf mice with wild type mice, and then to the far right is the p-value for whether the differences whether these amounts are different between groups. So what we can see is for all of these bile acids, with the exception of one, alpha muricolic acid, all of them are significantly higher in the dwarf mice when compared with the wild type mice. And not just a little bit higher, but a lot higher, ranging from 2.8-fold to 5.4-fold higher in the dwarf mice when compared with wild type. And you can see at the bottom too that total levels of these bile acids are 4.2-fold elevated in the dwarf mice when compared with the wild type. So from this, we can conclude that circulating bile acids are associated with an increased lifespan. Although the primary intervention was the mutation in the growth hormone receptor, bile acids, as we can see by this data, are associated with an increased lifespan. So what about causation? So in an earlier video, we saw that one of these bile acids, the primary bile acid known as cholic acid, was significantly higher in the dwarf mice, 3.5-fold higher in the dwarf mice when compared with wild type. And cholic acid on its own extends lifespan in a mouse model of accelerated aging, which is what we can see here. So in this study, they used the ZMP-STE24 knockout mice, and this is an accelerated aging model or a mouse model of progeria, which is accelerated aging, a genetic model of accelerated aging. So they split half these mice into control-fed and cholic acid-fed, CA. More specifically, 0.1% cholic acid was supplied in the diet. And what we can see by looking at median, so 50% survival, and maximum survival, which was defined as 20% survival. So in this study, it was 80% of the colony had died, only 20% was still alive. We can see a significant increase by 7% for median lifespan and a borderline significant increase for maximum lifespan, with the p-value for maximum lifespan being right at the borders. P-value equals 0.054. So what about other bile acids? We see that at least one bile acid can extend lifespan. What about other bile acids? Can they extend lifespan? So I think a good idea is to look at other bile acids on this list and to look into the literature to see if any of them have extended lifespan in other animal models. More specifically, what about lithocholic acid, which was 3.7-fold higher in the dwarf mice when compared with wild type? So first, we can see that lithocholic acid extends lifespan in yeast. So here we're looking at the percentage of alive cells or alive yeast cells on the y-axis against days in culture. So these are yeast cells grown in cell culture. And when looking at the wild-type yeast, these yeast were not supplied with bile acids, so that's the black squares as shown there. And when looking at median survival, again, 50% survival, half the yeast cells have died, half are still alive. We can see that median survival for the wild-type non-bile acid supplemented yeast was 12 days. Now notice there is a dramatic extension in lifespan, shifting the survival curves to the far right. And as you guessed it, lithocholic acid. So yeast that were supplemented with lithocholic acid, you can see there's a dramatic increase in median lifespan up to 30 days. So that's a 250-fold increase or 2.5-fold increase for median lifespan in lithocholic acid supplemented yeast. But note that this is when the yeast cells are grown under 0.2% glucose. And these are calorie-restricted conditions, as we'll see in a minute. So does lithocholic acid extend yeast lifespan without calorie restriction? And it does. As we can see by the title, lithocholic acid extends lifespan in yeast under calorie-restricted and non-calorie-restricted conditions. So what are we looking at here? So we've got lifespan on the y-axis, including both average lifespan on the left and maximum lifespan on the right. And then we've got the glucose concentration that the yeast cells were exposed to, ranging from 0 all the way up to, or 0.2% glucose, all the way up to 2% glucose, so 10 times higher than the data that I just showed on the previous slide. And then we've got the data for yeast that were not supplemented with lithocholic acid in the open white circles, and then the yeast that were supplemented with lithocholic acid in the black, in the filled circles. So when looking at 0.2% glucose, the data that I just showed on the previous slide, there was that increase in median, but also, as we can see here on the left, maximum average lifespan, mean lifespan. But then what I didn't show was there was also a significant increase in maximum lifespan, as shown in the right panel. All right, so what about under non-calorie restricted conditions? So from that, we go from the 0.2% supplemented media that had glucose in the media at 0.2%, and we go to 2%, so 10-fold higher, 10 times higher glucose level. What's the effect on lifespan in lithocholic acid versus non-lithocholic acid supplemented yeast? And we can see that even under non-calorie restricted conditions, 2% glucose, lithocholic acid supplemented yeast still had significant increases for both average and maximum lifespan. So that's why we can see LCA lithocholic acid extends lifespan in yeast under both calorie restricted and non-calorie restricted conditions. All right, so can lithocholic acid extend lifespan in other animal models? So for that, we go to flies, and lithocholic acid extends lifespan in flies too. So here again, we're looking at survival on the y-axis plotted against the age, so how long did the flies live? And this is data in male W1118 flies. I haven't come across any data for lithocholic acid supplementation on lifespan in female flies. If anybody's seen that data, please leave it in the comments so we can share the information. All right, so when looking at median and maximum lifespan, in this study being 50% survival for median lifespan, 10% survival for maximum lifespan, we can see significant increases in flies that were supplemented with lithocholic acid for both median lifespan and maximum lifespan. All right, so what about mice? Can lithocholic acid supplementation extend lifespan in mice? And unfortunately, I haven't come across that data yet. And again, if anyone's come across that data, please leave a comment. I'd be happy to make a video about that in the future. All right, so what about human data? Is there human data that suggests a role for lithocholic acid on longevity in people? So fecal levels of lithocholic acid are higher in centenarians, so people who've lived to older than 100 years, when compared with younger age groups. And we can see that data here. So we've got lithocholic acid, LCA, and that's micromoles per gram, micromoles of lithocholic acid per gram of feces, or how much lithocholic acid was in poop. And then there are 4 groups on the x-axis. So first, centenarians. In this centenarian group, there were 160 people who had an average age of 107 years. And then there were 3 younger groups. Older, which had an average age of 86 years, and there were 112 of those subjects. Young, which had an average age of 31 years, 41 of those subjects. And then CEL, which are lineal descendants, so offspring of centenarians, that had an average age of 75 years, and there were 22 of those subjects. And what we can see is that centenarians had significantly higher levels of lithocholic acid when compared with all of the other groups. So higher than the older group, higher than the younger group, and higher than their kids. Now let's take a sidestep as to why this may be important. And that's because relatively higher fecal levels of lithocholic acid suggests a role for gut bacteria on longevity. So why is that the case? So starting from cholesterol in the liver, cholesterol is degraded by a series of enzymatic steps to produce the primary bile acid, chino or kino deoxycholic acid, CDCA, which is then conjugated with either taurine or glycine to form tauro-CDCA or glyco-CDCA. Now, those metabolites, those conjugated metabolites, are then released by the gallbladder after a meal into the intestine, where gut bacteria convert it into either ursodeoxycholate, UDCA, or lithocholic acid, LCA. So, in other words, lithocholic acid is exclusively produced by gut bacteria. So, all right, this was one study that I showed you for lithocholic acid levels in poop in human subjects, higher in centenarians. Have other human studies replicated this finding? And there is indeed another study that looked at lithocholic acid levels in centenarians when compared with younger age groups. And that's what we're looking at here, lithocholic acid levels in feces or poop. So the 2 groups in this study were centenarians or close to centenarians, people in the 94 to 105-year-old age range that had an average age of 97 years, and their kids who had an average age of 67 years, 50 to 79-year-olds. And what we can see is that the centenarians, or close to centenarians, had a 43% higher level of lithocholic acid in feces when compared with their offspring. And this difference was statistically significant, as you can see by the p-value and false discovery rate, FDR, were both less than 0.05. All right, so with the goal of longevity, can levels of lithocholic acid be increased? And if so, how? Well, exercise may be one way to do that. And blood levels of lithocholic acid are increased after exercise. So this is after either 1 hour of endurance exercise or 1 hour of resistance exercise or strength training. So let's break down the data. So in this study, it was a very small study. It only included 10 people. And this study only included men. And again, if anyone's come across studies in women, please leave a comment. I'd be happy to share it with the community. So this was young men, 24 years old, lean, with a BMI of 23.7, so not overweight or obese. And when I say lean, we can see by the body fat percentage was 12.7%, which is lean. And these were fit subjects that had a VO2 peak of 55.7. So these are not average fitness people. This is a relatively high level of fitness. All right, so what was the endurance training protocol for those who are interested in trying to increase their own lithocholic acid levels, or at least reproduce the findings of this study? So there was a 10-minute warm-up on the bike, and then it was 50 minutes of biking at 70% of their VO2 peak. So a relatively strenuous 50-minute bike ride, not including the warm-up, but 1 hour of total endurance exercise. All right, so what was the effect of that 1 hour of endurance exercise on blood levels of lithocolate? So before exercise, lithocolate levels were 0.01 micromolar, and then 60 minutes after exercise, that amount was tripled to 0.03 micromolar, and it still remained elevated up to 3 hours after exercise at 0.02 micromolar, so doubled when compared with before exercise. So from this, we can see that lithocholic acid levels are increased up to 3 hours after exercise for endurance exercise. All right, so what about resistance exercise or strength training? So first, what was the strength training protocol? So there was a 5-minute warm-up on the bike, followed by 15 reps each for squats, push-ups, sit-ups, and back raises. And then the actual strength training protocol, aside from the warm-up, was 5 sets of 10 reps each for knee extension, bench press, hamstring curls, lat pull-downs, and leg press. All right, so what was the effect on lithocholic acid levels in blood? So again, starting from before exercise, they had 0.01 micromolar levels of lithocholic acid in blood, which was then tripled either 60 minutes after exercise and 180 minutes, so 3 hours after exercise. Blood lithocholic acid levels were tripled after this resistance exercise training protocol. So this then raises the question, is lithocholic acid levels, are lithocholic acid levels in blood higher in athletes when compared with sedentary subjects? And that's another one that I haven't come across that data, but if so, it could suggest that may be one reason why there's an increase in average lifespan for at least in animal models for exercise training when compared with sedentary animals. So if anyone's come across the athlete data and lithocholic acid levels in blood, please leave it in the comments. I'd be happy to share it with the community. All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Thanks for watching. I hope that you enjoyed the video. Have a great day.